Electrophilic substitution reactions. Replacement of a hydrogen atom in benzene ring of an aromatic compound by an electrophile or electron-loving species is known as electrophilic substitution. Electrophiles are electron-deficient species. They carry either positive charge or sometimes they are neutral, like Lewis acids. And such reactions are characteristic of aromatic compounds because aromatic compounds act as electron-rich centers. For example, benzene, naphthalene, anthracene, etc. undergo electrophilic substitutions. And the important examples for electrophilic substitutions are nitration, sulfonation, halogenation, Friedel-Crafts alkylation, and acylation. Mechanism of electrophilic substitution in benzene. The reaction follows bimolecular mechanism and it's a two-step mechanism. In the first step, the electrophile attacks benzene ring slowly to form a carbocation, which is also known as sigma complex, and this carbocation is stabilized by the delocalization of positive charge by resonance effect. And in the second step, which is the rapid step, a proton is expelled from the sigma complex to form the product. So the electrophile attacks the benzene ring, benzene as it is electron-rich center. In presence of the electrophile, an electromeric shift takes place, and this is the slow step, which is the rate determining step. Now the carbon becomes negative, and to the negatively charged carbon, the electrophile gets attached. And this is the structure of the resulting carbocation, and the positive charge can be delocalized through the benzene ring. And that is equivalent to this structure, and this is the sigma complex. So formation of the sigma complex is the slow and rate determining step, and in the second step, which is the fast step, an H plus is expelled, and we get the substituted product. Nitration of benzene. Replacement of hydrogen atom of benzene ring with a nitro group is known as nitration. When benzene is treated with nitrating mixture, which is an equimolar mixture of concentrated nitric acid and concentrated sulfuric acid, nitrobenzene is formed. And in nitration, the electrophile is nitronium ion. Nitronium ion is formed by the action between concentrated nitric acid and concentrated sulfuric acid. The nitronium ion, which is the electrophile, that attacks benzene in the slow and rate determining step to form the sigma complex, and from the sigma complex a proton is subtracted by the bisulfate ion HSO4- to form nitrobenzene. The intermediate carbocation is resonance stabilized. And we can represent it as the sigma complex. The bisulfate ion abstracts proton from the sigma complex, which is the first step. Halogenation of benzene. Replacement of hydrogen atom of benzene ring with a halogen atom is known as halogenation. When benzene is treated with chlorine or bromine at ordinary temperature in presence of halogen carriers like iron, ferric chloride, etc., halobenzene is formed. For example, when benzene is treated with chlorine in presence of iron, we get chlorobenzene. And the extent of halogenation depends upon the amount of halogen added. And the electrophile in halogenation reaction is the halonium ion X+, where X can be chlorine or bromine. Mechanism of halogenation. halonium ion is formed by the action between halogen and ferric chloride. For example, when chlorine is treated with ferric chloride, as ferric chloride is a Lewis acid, it accepts a Cl minus, so we get Cl plus chloronium ion plus FeCl4 minus. And the halonium ion, the electrophile, attacks benzene ring in the slow and rate determining step to form the sigma complex, from which a proton is abstracted by the anion FeCl4 minus to form halobenzene. So the electrophile Cl plus attacks benzene ring in the slow step. Electromeric shift takes place and we get an intermediate carbocation, and this carbocation is resonance stabilized. And this is equivalent to the sigma complex. The proton is expelled. And we get the product chlorobenzene. Sulfonation of benzene. Replacement of hydrogen atom of benzene ring with a sulfonic acid group is known as sulfonation. For example, when benzene is heated with fuming sulfuric acid or oleum at 80 degrees Celsius, benzene sulfonic acid is formed. And the electrophile in sulfonation reaction is a neutral electrophile, that is sulfur trioxide. And unlike nitration or halogenation, sulfonation reaction is reversible. Mechanism of sulfonation. The electrophile sulfur trioxide is present in the acid itself as a result of the equilibrium. And the electrophile SO3 attacks rapidly to form the sigma complex, from which a proton is abstracted slowly by the bisulfate ion to form benzene sulfonate ion, and benzene sulfonate ion is then protonated to form benzene sulfonic acid. So sulfur trioxide, it's an electron deficient compound and its structure can be written as sulfur trioxide attacks benzene, and this is a fast step. And that leads to the formation of the sigma complex, which is a resonance hybrid of 3 contributing structures, as we have already seen. And the bisulfate ion in a fast step abstracts proton from the sigma complex and we get benzene sulfonate ion, and benzene sulfonate ion is protonated and we get benzene sulfonic acid. Friedel-Crafts reaction: replacement of hydrogen atom of benzene ring with an alkyl or acyl group by treating with an alkyl halide or acyl halide in presence of Lewis acid catalyst like aluminum chloride is known as Friedel-Crafts reaction. For example, when benzene is treated with, say, methyl chloride in presence of anhydrous aluminum chloride, Lewis acid catalyst, we get methyl substituted benzene, and that is toluene. Another example, when benzene is treated with, say, CH3COCl, an acyl halide in presence of anhydrous aluminum chloride. Acyl group is RCO group. So we get acyl substituted benzene. Here it is COCH3, and that is acetophenone. So alkyl substituted and acyl substituted benzenes can be prepared using Friedel-Crafts reaction. Friedel-Crafts alkylation mechanism. So alkyl halide forms a 1:1 complex with the catalyst AlCl3. For example, RCl forms a complex with AlCl3 having a structure like this, RCl plus AlCl3 minus. And this complex, it can break into R plus, that is carbocation, plus AlCl4 minus. And in the alkylation reaction with primary alkyl halides, this Lewis acid complex is the electrophile, whereas in the alkylation with secondary and tertiary alkyl halide, the alkyl carbocation, that is R plus, is the electrophile. The electrophile attacks benzene in the slow and rate determining step to form the sigma complex, from which a proton is abstracted by the anion AlCl4 minus to form toluene. So this is the Lewis acid complex that attacks benzene. The sigma complex is formed which is resonance hybrid, and the sigma complex then in the first step gets converted into the alkyl substituted benzene plus AlCl3, the catalyst is regenerated. Friedel-Crafts acylation. The acyl halide forms 1:1 complex with the catalyst AlCl3, which undergoes dissociation to form acyl carbocation, which is the electrophile in acylation reaction. For example, RCOCl, acyl halide, reacts with AlCl3. A Lewis acid complex having the structure is formed, which then dissociates to RCO plus acyl cation plus AlCl4 minus, and the acyl cation is the carbocation in Friedel-Crafts acylation. For example, CH3 CO plus. If the acyl halide taken is CH3COCl, then the electrophile is CH3CO plus. So the electrophile attacks benzene in the slow and rate determining step. We get the intermediate sigma complex, which is resonance stabilized. And in the first step, AlCl4 minus abstracts a proton from the sigma complex, and we get the final product, the ketone. Here it is, acetophenone. So Friedel-Crafts alkylation and acylation reactions are having great synthetic utility because it is used to prepare a wide variety of alkylated and acylated benzene derivatives.